Today we are talking about hypothesis testing and the t-test. Add that in. All right, so this is a combination of two lectures actually, because it just made sense to talk about them together instead of separately. Because hypothesis testing is the process that we go through for researching a research question, for carrying out a research question or testing a research question. And part of that process is that we run a statistical test, and a t-test is one of those tests. So I thought it would make sense to, while describing the process of hypothesis testing, that we also examine one of the statistical tests we use in that process. This is actually kind of a hard lecture for me to make. It took a while just because there's a lot of information when it um, comes to running one of the statistical tests, like the t-test. And the information can be separated into the conceptual information, like what you need to know about what the t-test is and how to use it and when to use it and when not to use it. And then the other part is the math part, more the technical part of it, of how do you compute the t-test, what are the formulas, what type of calculations do you use? So that part we won't be going into as much for today's lecture. We'll focus more on the conceptual part of the t-test because a lot of the math stuff will be run by usually software. So a lot of researchers and statisticians don't do the math themselves when they run these tests. They just use the software for it. But it's really important to know the conceptual part, just because you want to know what the test is and when to use it, so you're not using it inappropriately or you're you know, not misinterpreting it or misusing it, because then the results aren't valid. Okay, let's jump right in. All right, so here's the outline. And it says hypothesis testing, but we should also say test. Usually when you have a name of a test like this, you usually italicize it like that, like the z-test or the t-test. Okay, we're going to talk about why we need it, what is it, when to use it, and how do you compute it, just like the previous formats. All right, so why do we need it? So far, we have learned that what we do in research, the idea is that we're working with a sample, a smaller subset of the target population, and then we want to generalize our findings in that sample to the target population. And hypothesis testing is a process for doing that. So hypothesis testing includes a specific statistical procedure that allows researchers to use the sample data to draw inference about the population. All right. And often we want to know whether there's differences between groups. And that's when the independent sample t-test comes in. And we'll talk a little bit more about what that means. But here are some examples of research questions involving group differences. Does the medication group have a better outcome than the control group? Does have a better outcome than the control group? See, these are two groups, right? One group gets the medication and one group gets it's control that gets a placebo. That's not a medication, maybe a sugar pill. Do people who smoke have higher rates of lung cancer than those who don't? Again, we're comparing two groups. One group is those who smoke, and the second group is those who don't. And we try to find the difference. Do people who sleep 8 hours or more have less wrinkles than those who sleep less than that? Again, two groups. One group is people who sleep 8 hours or more, and one who sleep less. And you can see why these are important research questions that we want to investigate, right? It has real world implications for health and best practices or recommendations for how people can improve their health and whether they should take a certain medication and whether they should quit smoking or whether they should sleep more or not. Okay, so what is what is it? Let's start with hypothesis testing. So hypothesis testing is a statistical method that uses sample data to evaluate a hypothesis about a population, typically used in a research study. So for example, going back to one of the previous example, if my hypothesis is that if people have more wrinkles if they sleep less than 8 hours. So that's the hypothesis. Then we had to put this down into two types of hypothesis. One is the null hypothesis and one is the alternative hypothesis. The null hypothesis would be there's no difference between these groups, meaning there's no difference between people who sleep less hours versus people who sleep more as far as how it relates to wrinkle development. The alternative hypothesis, which is the one that we're interested in, right? The one that we're testing, is that there is a change or difference in that for people who sleep more than 8 hours, they have less wrinkles than the other group who sleep less than 8 hours. So anytime you think about research question, it's really important that you put it in this type of hypothesis format. The null hypothesis, meaning there's no change, there's no effect, and the alternative hypothesis, which is what you're interested in testing. All right, alpha level is really important to talk about. This is the level of significance you want to test. So alpha level, the best way to think about this is that anytime you're doing research with a sample, the results may reflect real world differences, or they may be due to chance. During the last lecture, we talked about probability, that there's probability related to z-scores. Some things have more probability than others. And so if you think about probability when it comes to research, is that your finding that you find in your research study, maybe part of it may be due to chance. And so part of the research process is to quantify how much of a risk you want to take, how much of a chance you want to take. So typically, very often, we use an alpha level of 0.05 in research, meaning that we are willing to take a risk and say that there's a 0.05% chance that our findings are due to chance or due to a random effect. So this will become more clear later as we talk about the alpha level, but just know alpha level is what we as researchers select ahead of time as far as how much risk or chance we're willing to accept. Okay, statistical significance. This is related to alpha level. This is what was called the p-value. I forget what P stands for, but basically this is very, very important and very common in research to talk about. It means whether your findings are significant or not. And so usually people say p-value of less than 0.05, meaning you have a significant finding, and you have a p-value of more than 0.05 means you don't have a significant finding. That means there's no treatment effect, that the research didn't work out, which is sad. Okay, so how do we interpret what this p-value means? Okay, when you run any type of test like the t-test, you will get a p-value. It'll tell you the p-value is 0.01, 0.03, 0.05, 0.16, 0.17, etc. And basically what you want to do is you take that p-value and then you put it into one of these categories. If the p-value is less than 0.05, you can say your finding is significant and that you have some type of significant research effect. If the p-value is greater than 0.05, let's say it's 0.051, 0.056, 0.06, 0.07, that means your results were not significant. So you didn't find what you were looking for in your research. So let's take the example of the increased sleep and its impact on the wrinkle formation. If I think that these two groups, if I believe that these two groups, the one that sleep more than 8 hours versus the one that sleep less than 8 hours, if I think there's a difference in wrinkle formation, then and if I run the tests and compare these two groups and the p-value is less than 0.05, I can say that there's evidence that there is a significant difference between these two groups, meaning that there is that people who sleep more than eight hours have significantly less wrinkles than people who sleep less than 8 hours a night. Conversely, if I run the t-test and I get a p-level that's greater than 0.05, then I can't say that there's a difference between groups, and then so I can't say that there's not enough evidence for me to say that that people who sleep more than 8 hours have any difference in wrinkle formation than those who sleep less than 8 hours. So two groups are not different, or as we say, not significantly different. So this word significant just means whether the p-value is less than 0.05 or greater than 0.05. And that's really important, just because that's how we determine whether the results from our sample can be generalized to the population. If your results are less than 0.05, then we say, yes, I'm working with a sample with people who sleep less than 8 hours and more than 8 hours, but if my results are significant, I can say this, even though I'm working with a sample, I could apply this finding to the whole population that I'm studying. So it's not just that if it's the p is less than 0.05, it's not just that people in my sample have less wrinkles when they sleep less than 8 hours, but I could say in the general population, is this true that people who sleep less than who sleep more than 8 hours have less wrinkles than people who sleep less than 8 hours. And again, that's only if the p-level is significant. That's really the value in doing these types of significance testing, is that you can extend your findings to the population. So you could say this applies more generally to people than and not just to your specific sample that you're looking at. So with any type of statistical tests, actually, I'm going to move this because we're talking about hypothesis testing here. So I don't want to put this part about t-testing in this slide. So I'm going to move it t-test. Move it here. Okay. All right, so 2 points to be aware of. We're not going to be talking about this much right now because it becomes more important as you talk about more and more statistical tests. But there's always a chance that what the results of your tests may show is significant, but it may not be significant. This is called type 1 error. And so what this means is that you may think that there's a difference in groups and your statistical test shows that, but this is false. It's called a false report. And when does this occur? It occurs when you may have a very extreme or non-representative sample. As remember in previous lecture, we said when you're working with a sample, you want to make sure it represents the population that you want to extend the findings to. And the alpha level 0.05 applies here because it says that there's a 5% chance that you may find a significant finding when there isn't one. That's how the alpha level relates to this. That's where you as a researcher saying, okay, I'm willing to take a risk and say, I'm willing to take a risk and say maybe like 5%. My finding has a 5% chance of being false, even though it shows it's true. Type 2 error is the other type of error occurs when you fail to reject the null hypothesis when it's really false. That means that there may be a significant difference in your group, but your test doesn't show that. My t-test, there could be a real difference between these two groups, between people who sleep a lot versus those who don't, but my test can't detect that. And there are a number of reasons for this. One of them could be maybe your sample size isn't big enough, or maybe the difference between these two groups is really small. And if those differences are small, your test may not pick up on that. So again, just something to be aware of. This is that sometimes the statistical test, the results aren't always correct. And And so this is usually what happens when you're working with statistics and research, is that you can't always be 100% certain your findings are true. But you're making a calculated risk here, and you're saying, at least I'm going to say, I'm going to say I'll take a 5% chance of that risk. And that's how we quantify it, and that's how we're able to make this research a science, is by saying, even though there's a risk, there's always a risk, because if you're working with a subset of a population, you would never know for sure whether your finding reflects the true population. The only way to know 100% whether your findings reflect the true population is to do research on the true population. Is to do, you're testing for all adults, you have to do the research on all 400 million adults in the US. That's the only way to be 100% sure. But you're ever working with a smaller sample of like even a couple of 100,000 people or a couple of 100 people, there's always this risk that your results may not match the population. And research and these statistical tools allow us to quantify that and minimize those risks. All right, here's a metaphor for hypothesis testing, because sometimes it can be confusing when you're thinking about the null hypothesis and the alternative hypothesis. And so the metaphor that I'm going to talk about is a jury trial. If you all have ever been in a jury trial, maybe you've been asked to be part of that as part of, what's that thing where you get called once every few years to participate in the jury? Yeah, I don't remember, because I always get called, but then I never get selected. Okay, well, as you know, everybody in the US have to participate in jury trial, and you get randomly called every few years, and you sit a jury, and then the two lawyers for the defendant and plaintiff argues their case, and then in the end, the other juries have to decide whether the defendant is guilty of the crime. Okay, so how does this compare to hypothesis testing? All right, so with hypothesis testing, you begin with a null hypothesis stating that there's no treatment effect or there's no difference between groups. So let's return to the sleeping example. You begin with a null hypothesis saying there's no difference between those who sleep more and those who sleep less. There's no difference in the amount of wrinkles that they have. So in the jury trial, it's the same thing. The judge says that you have to assume the defendant did not commit the crime. You have to assume innocence until proven guilty. So the second part is in the hypothesis testing process, is that the researcher gathers evidence to show that the treatment actually does have an effect. So you're refuting the null hypothesis. So the evidence here is that you're gathering people, you're surveying them or whatever you're doing, and then you're writing your tests. And then, you're looking at the p-value, the significance value. That's your evidence. So if your p-value is less than 0.05, then you could say that there's a significant difference or significant treatment effect. And that when you say that, that means you're refuting the null hypothesis. The null hypothesis meaning there's no difference. So how that relates to jury trial is that the police has to gather evidence to show that the defendant really did commit the crime. So the police are trying to convince the jury to let go of the assumption that the defendant is innocent. They're trying to gather evidence to refute that assumption and to show that the defendant is guilty of a crime. All right, the next phase. If there's sufficient evidence, the researcher rejects the null hypothesis and concludes the treatment effect exists. Yeah, we just talked about this. So gather enough evidence, run the test. If P level is less than 0.5, you could say there's a significant difference. And then you could accept the alternative hypothesis, which is that there's significant difference between the groups or there's significant treatment effect. How this relates to jury trial is that if the police provides enough evidence, the jury then rejects the null hypothesis and concludes that the defendant is guilty of the crime. So alternatively, if there's insufficient evidence, meaning you gather the evidence, you run the test, and the results are not significant, the p-value is greater than 0.05, then what we say, this sounds confusing, but what we say is that the researcher fails to reject the null hypothesis. That means that there's insufficient evidence to conclude that treatment exists or that there's a significant difference between the groups. that's just technical language. Technically, that's the most accurate way of saying this, but not a lot of people say that. A lot of people say whether there's a significant effect or there's not a significant effect. The significant effect if the p-load is less than 0.05, there's not a significant effect if the p-load is greater than 0.05. But a lot of people say the researcher fails to reject the null hypothesis. That's the most technically correct way of saying that. Same thing with the jury trial. If there's not enough evidence, the jury finds the defendant. The jury fails to find the defendant is guilty. That doesn't mean that the defendant is not guilty. Maybe they could have committed the crime, but really the point of the jury is for the police to show that enough evidence to prove beyond a reasonable doubt that this person did commit the crime, and there's no other plausible explanation, right? But if there's not enough evidence, then even if the jury may think that the person committed the crime, they may feel that the person committed the crime, they need to think of the specific piece of evidence to really back up that opinion. Okay. Same thing for the p-value. Even the p-value is greater than 0.05. We don't say that there's no treatment effect. We don't say there's no treatment effect because maybe there's a treatment effect, but we just can't find the evidence. So what I would say is, I would rewrite this and say insufficient evidence to include a treatment effect exists. Oh, this is correct, because it's not saying that there's no treatment effect. It's saying that we don't have enough evidence to say that there's a treatment that exists. Yeah, and the reason why we want to make this point really clear is that maybe there is a significant difference between these two groups, but for a lot of reasons we're not able to find that in our test. Maybe because our sample size is too small, maybe because the difference is so small we can't pick it up with the test. But we don't want to rule out that there's no difference. We want to say that we don't have enough evidence, or based on the research, we couldn't find enough evidence to show that that's a significant effect that exists. Okay. Let's talk about, so we just talked about hypothesis testing. Let's talk about t-test. So hypothesis testing involves a statistical test, and one type of statistical test is the t-test. And one type of statistical test is t-test, yeah. And there's a lot of statistical tests. There's the z-test, which we learned about. There's the correlation, which is a test. There's ANOVA, the structural equation modeling, there's multi-level modeling. So there's like so many tests that you can use, so many statistical tests that you can use in your hypothesis testing process. We're going to learn about the t-test because that's one of the most basic, I would say, tests that you could use because it has a very simple design. And so even with the t-test, there's three types of t-test. There's the one sample t-test, the independent actually, this ordering is wrong, so let me fix this order. This should be number 3. And this should be number 2. Okay. All right, 3 types of t-test. There's a one sample t-test, a paired sample t-test, an independent 2 sample t-test. Also called independent sample t-test. We'll just call it that, just for shorthand. Okay, what is the one sample t-test? The one sample t-test is, you have, like the name implies, you have one sample, one group that you're working with, and you're trying to find if the mean of this group is different from the mean in the population. And this is the formula. So T, and you don't have to remember these formulas, because even though we're talking about 3 t-tests, we're only going to be really exploring or talking deeply about the last one, the independent sample t-test, because this is the one that's most commonly used. These other 2 aren't used that often. The second one is used more often than the first one, but definitely the most common t-test is the independent sample t-test. Okay, so the one sample t-test means you want to have one sample and you get a mean. For that sample, you want to know if that mean is different from the population. So let's look at an example. If I'm doing a study, I have a sample of 300 PAU students. and I found that they drink a mean of 3 cups of coffee a day, I could use the one sample t-test to test the question, is this different from the mean number of daily coffee drinks seen in the general population, which has 332 million in the US? So that's, you see here, we have a mean from the sample, and we want to test to see if that's different from the mean in the population. Okay. Next type of t-test is the pair sample t-test. Again, you have one group only, and you want to see if that group changes over time. And so back to the coffee example, I have my 300 PAUs students, and they drink a mean of 3 cups of coffee a day. Let's say I implement a program, a social media campaign to reduce coffee intake. Maybe talking about the harms of drinking too much coffee, how it negatively impacts sleep or drowsiness, etc. So I could use the paired sample t-test to test this question. Does the mean coffee intake for the sample change before and after social media campaign? Basically, I'm taking the sample and then I'm measuring them at 2 different time points and looking at the mean coffee before and the mean coffee after the social media campaign and see if there's a difference. And if there's a difference, then I can conclude that my campaign was successful for reducing coffee intake. But if there is no difference between the before and after, then I could conclude that there's not enough evidence to show that the campaign was effective, or saying that the campaign was the effect of the campaign was not significant in reducing coffee intake. Okay. So again, one group, you measure them at 2 different times, take the mean of both, and then see if there's a difference. The independent sample t-test, this is the one that we'll be focusing on for the homework, the in-class exam, exercise, the test. The purpose of this is to compare the means of 2 groups. So here we have actually 2 groups of people, 2 different groups of people, and we'll take the mean of one and the mean of the other and compare them and see if there's a difference. There's a formula. We'll return to this formula in just a few minutes. And this is how we would apply this to the example we've been talking about. We have the 300 PAU students who drink 3 cups of coffee a day. And then we want to know if this number of coffee for PAU students differ from another group, let's say 300 UC Berkeley students. So we take the mean of both, and then we do the t-test, and we find if they are significantly different or not. And so here you see there's 2 separate groups. That's why it's called independent sample t-test, because these 2 groups are independent. They're separate people. We're not measuring them one group over time. We're measuring 2 completely different groups of people. And so with the independent sample t-test, whatever result you find, you can generalize to the population. So I may be doing this test on 300 PAU students to 300 UC Berkeley students. But if I get a significant difference, let's say PAU students drink more coffee than UC Berkeley students, then I could say that, okay, this result probably applies to the entire campus, entire population of both campuses. Let's talk about assumptions. So all statistical tests have assumptions. Assumptions mean there are things that about the data or about the sample that needs to be met in order for you to use this test. So one is random sampling, meaning that everyone in the PAU campus and everyone in the UC Berkeley campus needs to have a equal chance of being selected for the study. Meaning that if I want to select the 300 PAU students, one way I can randomly sample them is getting the list of all the students, maybe getting a big cell list and just randomly picking out 300 students. And that means that each one of those students on the list has an equal chance of being selected for this research. That's what the random sampling means. There needs to be independent observations in each group. That means each person in each group needs to be unrelated to other people in that group. By unrelated, I meaning, like, for example, you can't have this one person provides 2 data points in the sample. For example, everybody needs to provide 1 data point. Another way of thinking about unrelated is that there can't be any specific relationship between the people in the group. Yeah, I don't know how else to put this without giving more specific examples, but we'll probably return to this point in a future lecture, and I could expand more on that one. There needs to be a normal distribution in both populations, meaning that coffee drinking needs to be, when you're looking at the histogram, within the population, it needs to be normally distributed. Not in the sample specifically, but in the population. So in the actual campuses of all the students on both campuses, the coffee drinking has to be normally distributed, has to create a normal distribution in the histogram. All right, and the variance for both population group must be equal, meaning that you remember standard deviation or a variability, meaning how much variance is in the scores. So coffee drinking needs to, the amount of variability of coffee drinking in the UC Berkeley campus needs to be about the same as the amount of variability in the PAU campus in coffee drinking. Not the sample, but in the population. Okay, so these are assumptions. Just something to be aware of. Conceptually, this is important. But as far as the computations, usually for the computations that we're doing this class, I will let you know when if the data or the sample you're working with meets these assumptions. And if you're running across them in the tests and the exams and the homework, they're going to meet these assumptions, or I'll make it explicit. Okay, so when is it used? So again, returning to the same point as before, hypothesis testing is used to determine whether results obtained from our sample can be generalized to the target population. And we can use the p-values to help us make that determination. And when you use the independent sample t-test, you use it when you want to test whether two groups differ on a specific variable, like coffee drinking or amount of wrinkles. How do you compute it? Okay, so hypothesis testing. Hypothesis testing involves these 4 steps, and then the t-test comes into step 2. So hypothesis testing, basically you have to state the hypotheses for your research question, and then you compute the test statistics or the statistical tests. Then you make a decision, and then you write up the results. That's the 4 steps of hypothesis testing. But I'll interweave how the t-test could apply into each of these steps. But the reason why I want to make this distinction between hypothesis testing and statistical tests is that you can use a lot of different statistical tests and hypothesis testing. So these 4 steps for hypothesis testing, you could use a z-test, you could use a correlation test, you could use a ANOVA test. And so that's why I want you to think about hypothesis testing in these 4 steps, and then think about the statistical test as an example of how you could input it in within each of these steps. Okay, so step 1 of the hypothesis test. Then you have to state the null hypothesis, you have to state the alternative hypothesis. Again, the null hypothesis means H0, H sub 0, that just means null, and H stands for hypothesis, null meaning 0. Mu1, that's the U is Greek for mu1 minus mu2 equals 0. This just means that remember, mu is the mean of the population. The mean of the population of population group 1 minus the mean of population group 2 equals 0, meaning that the 2 groups in the population are not different or not significantly different. That's why they're equal to 0. And that's why we say for the why we interpret it in this way. For the population, there's no significant difference between the groups. So conversely, the alternative hypothesis, this is usually the question or the hypothesis that you're testing. That's what you're interested in. You're saying H1 meaning hypothesis 1 or the alternative hypothesis. Mu1 minus mu2 does not equal 0. That means that the mean of the group 1 in the population minus the mean of the group 2 in the population does not equal 0. So it's equals to a positive value or negative value. That's what not equals 0 means. And that just means that there's a difference, right? If you're subtracting these 2 group means and there's not a 0, that means there's a significant difference between these 2 groups. So the way you interpret this is for the population, there's significant difference between the groups. All right, so you state the hypotheses. and then you compute the test statistics. So in this example, when you're working with a t-test, you're using a software like Google Sheets for this. And there's many types of statistical software you can use to test different types of tests. There's Excel, there's SPSS, there's R, there's Python. So for this class, we're using Google Sheets. Once you get to more of the advanced statistical tests, Google Sheets won't be able to handle it because it's not built as a statistical software, it's built as a database. But for the sake of this class, we can use the Google Sheets. Okay, so after you run the test, then you have to make a decision. Is your finding significant or not? And again, we're looking at the p-value, right? Your p-value is less than 0.05. You say that your results are significant, and you say that there's a difference between the groups based on the t-test. If the results are greater than 0.05, then you say there's no significant difference. That's why I have a happy face if it's less than 0.05 and a sad face if it's greater than 0.05. So a lot of times whether your study gets published or not, you submit, you can do a research project for months or years, and it could come down to a single p-value. It comes down to whether the medication improved depression or not, or whether exercise improves sleep or not. And you can do this really elaborate research study, and it could all come down to a single p-value. And if your p-value is less than 0.05, it will get published. If it's greater than 0.05, it won't get published. So the p-value in research is, there's a lot of controversy about it. About some people think it's overblown and that we're making too much focus on it. But when it comes to getting published and whether your research is talked about in the news or cited, this is really what it comes down to, what matters the most. Well, sometimes some research studies have a lot of different tests that they're running. They're making a lot of different comparisons or doing a lot of different treatments, and so they can have many p-values. So in that case, if one p-value doesn't work out, you could rely on the others to hopefully get your study published and out there. Okay, the last step of hypothesis testing is that you want to write up the results in APA format if you're submitting to a psychology journal. Other journals have their own formats. Okay, so when you're using a t-test, you want to include all these essential elements. One is the mean and standard deviation of each group. 2 is the t-statistic value. 3 is the p-value, also known as significance value. 4 is the effect size, which is the confidence interval, the variance explained measure, which is R-squared, or the Cohen's d. We'll talk a little bit more about these effect size measure. So here's an example of a write-up that you would see in a journal. Participants in the treatment group reported fewer episodes of major depression compared to participants in the control group over the past year. So here, this is a study where there is some type of treatment, maybe a medication treatment, and it's given to 2 groups of people. One group, the medication is given to one group, and the other group gets a placebo. They don't get any medication. And then they compare to see afterwards whether there's reduction in depressive episodes over the last year for those who receive medication versus those who don't. So you see here, you see here that there's a mean and standard deviation of the first group. So this part of the sentence talks about the first group. The participants in the treatment group reported fewer episodes of major depression. So here, because this goes after this treatment group, the treatment group had a mean of 5.64 depressive episodes and a standard deviation of 1.15. So this part of the sentence compared to the participants in the control group. So this tells you that this is the mean and standard deviation for the control group. Actually, what I did here is correct, but you could even move this and put it here closer to where it says treatment group. So that way it's even more clear that this mean and standard deviation applies to the treatment group. So the control group had a mean number of depressive episodes is 8 with a standard deviation of 0.96. Okay, continue on. The mean difference in episodes of depression between groups was large and significant. Okay, so you see here's the t-value. This is the degrees of freedom, which actually we should put here too. T-statistics and degrees of freedom. And we'll talk about what all these terms mean in a little bit. So T-statistics is negative 5.88. The degrees of freedom is 26. The p-value is less than 0.01. The Cohen's d effect size is negative 2.23. So you see here, when you write up the results, you want to say what you found, and you want to provide the numbers, the statistical numbers, which is the evidence of your findings. Because just by saying it is not enough. You have to back up what you're saying with evidence. And the evidence we're using here is the statistical result, which is what all these numbers mean. You see here, p less than 0.01. Usually you would say like, you would say the specific p value. Yeah, p equals 0.01 or 0.02 or whatever. Okay. And you see, because it's 0.02 is less than 0.05, you could say this finding was significant. All right, how do you compute the t-statistic? Sometimes you call it the t-test, it means the same thing. So I broke this up into two sections. One is the section that you don't need to know because it's computed automatically by the software, by the Google function. The other section is that it's the side that you do need to know because it's not computed automatically. We have to do this by hand. And the t-statistic, the math is kind of complicated, so that's why I'm not going to have you do it. And because in practice, in the real world, if you ever run the t-test, you never need to do it by hand. So why would I need to make you do this if you don't need to do it in the real world? Okay, so first you compute the degrees of freedom and the sum of squares. Degrees of freedom basically is a sample size, and they adjust it by subtracting 1. So it's a little bit more complicated than that, but for the sake of this class, is what you need to know. So the degrees of freedom for the DF1 means degrees of freedom for group 1 is the sample size in group 1 minus 1. DF2 is the sample size in group 2 minus 1, basically. And so the degrees of freedom for the t-test is just the 2 degrees of freedom added together. All right, so next you need to compute the poor variance. Remember, the variance is the standard deviation in each group. And so for the t-test, it's the standard deviation in each group. And yet if you square the standard deviation, then you get the variance. So in a t-test, you have to compute the poor variance, which is just the combined variance of both groups. And this is the formula for it. Basically, you add the 2 sums of squares for each group, and you divide it by the 2 degrees of freedom for both groups. All right, and then you have to compute the standard error for the mean difference. So the mean difference is the difference between the 2 groups in your sample. The standard error, what the standard error means or stands for, is basically the amount of expected discrepancy between the mean in your sample and the mean in the population. You remember how we say that there's always, when you're working with a sample or a subgroup from the population, there's always going to be a difference between your mean and the mean that's in the population. So the way we quantify that is by computing the standard error, which is what we see here. Okay, and then finally, after you compute all that, you can compute the t-statistic, which is what this is, the formula is. So you see here, you need all these steps in order to finally get to the t-statistics. First, you need to compute the degrees of freedom before you could get the poor variance, and then you need to compute the poor variance before you could get the standard error, and then you need to compute the standard error before you can compute the t-statistics. And that's why it's important to know all these different elements. All right. So again, that you don't need to do. I'm just telling you that so you know the concept behind it, but you don't need. I won't ask you to compute any of these things by hand. What you do need to compute by hand is the effect size measure. So what effect size means is that is how big is the difference between your groups. So earlier we talked about the p-value. The p-value tells you whether your finding is significant or not, whether you publish, whether this really is a difference between the group. But that doesn't say how big the difference is. Does that mean that because the difference could be small, it could be medium, it could be very large. The p-value doesn't tell you. It just tells you there is some type of difference between these two groups. And so it's also important, in addition to that, you need to provide information about how big is this difference. And that's what the effect size measure does. And there's two types. I mean, there's more than two, but we'll just use two for the sake of this class. There's the Cohen's d, meaning it's the magnitude of the difference. And how you compute that is you subtract the mean of both groups, mean 1 minus mean 2, and then you divide it by the square root of the pooled variance. So the pooled variance is this value, and so you take the square root of that, and you divide the difference between the two means. And then you get a d value. The d value using could be from 0 to 1.5 or 2. But these are the three different levels, three different categories. The d value is small if it ranges from 0.2 to 0.49. It's medium, it ranges from 0.5 to 0.79. It's large if it's 0.80 or up. And d is really what it stands for is the standard deviation in the mean difference. So usually what you would do is you compute this d value, and then you report it in your results as either small, medium, large. And you go back, let's go back to the previous slide. You see here that this d value is negative 2.23. That falls into the large effect. So I could say, actually, this is all positive, but I'm going to say no. It could be negative as well. D values going to be negative. If it's negative, just take away the negative and put it in this category. Since this is d value over here is negative 2.23, you see here that's, how do I do plus or minus? I don't know. You could say here that's larger than, that's extended above the range of 0.80. Let me see if I can put plus or minus. Insert symbol. Special characters. There you go. Plus or minus. There you go. Perfect. Okay, perfect. All right. Yes, the Cohen's d value is sometimes it's just listed as d, sometimes listed as Cohen's d, but you can see here if it's within these ranges, you could categorize it as small, medium, large. This is important because a lot of times the finding could be significant, but it's really small, so it doesn't matter. If there's if the difference between the medication group and depressive episodes is really small, let's say they only have one. Let's say they have like the medication group has 3 depressive episodes and the control group has 1 depressive episodes. I mean, it has 4 depressive episodes. So really, it's only improvement in 1 depressive episode. And is that helpful, or maybe. Let's say the medication group, let's say the control group had 50 depressive episodes in a year, and the medication group have 49 depressive episodes. So really, it's only improvement 1. But when you look at the scope of how many depressive episodes people are having, 1 less out of 50 is not really that big of a deal. So That's why you want to say, oh, it's a small effect. So the reader would know, okay, this maybe doesn't really matter, even though it's significant, maybe it doesn't really matter that much. All right, explain variance. So this is an interesting concept. And so this is also another effect size measure. And so it measures the percentage of variance accounted for by the treatment and indicates whether the effect size is small, medium, or large. Percent of variance meaning how much the treatment is responsible for improvement. Let's say the treatment, let's say, let me think. Let's say people improved in the depressive episodes by a lot. Let's say there's a reduction in 10 episodes each year for the people who take the medication. You could also estimate a number and say the medication was responsible for that 50% of that improvement, or 75% of that improvement, or 80% of that improvement. That's what these values means. 0.01 to 0.08 means they have the medication accounted for 1% to 8% of the improvement. 0.09 to 0.24 means they accounted for 9% to 24% of the improvement. 0.24 larger means they accounted for 24% or larger or more of the improvement in depressive episodes. So for some people, this is more intuitive to think about. It's like how much does the treatment accounts for the improvement or the change. But either one, and you could, for the t-test, you could put either one. I'll probably ask you for the Cohen's d because that's more common to be put in the t-test. Okay, let's do a example problem. This is the last part of this lecture. So look at this. Look at this problem. The background. You hypothesize that people who use social media before bed will go to sleep later, which will result in a shorter duration of sleep. You also believe using social media close to bedtime will disrupt sleep quality, further reducing sleep duration. You want to test this hypothesis by conducting a study. You gather a sample that includes two groups of people. In group 1, there are 14 adults who use social media within an hour of their bedtime. In sample 2, there are same number of adults, 14, who do not use social media within an hour of their bedtime. You want to test your hypothesis that using social media within an hour of bedtime will reduce sleep duration by showing that group 1, the one that uses social media close to bedtime, has significantly lower sleep duration than group 2, those who do not use social media close to bedtime. Okay, so that's the study design. So here are your instructions. You are to use a independent sample t-test to test whether there is a significant difference between the two groups. For this test, you want to use an alpha level of 0.05, a two-tailed t-test, and assume both groups have equal population variances. Remember, this is assumption of the t-test. And so I'm telling you right now that they have equal variances, so you don't have to worry about it. Two-tailed t-test, we haven't talked about that. So all you need to know right now is that this, when it comes to t-test, you can either do a one-tail or two-tail t-test. And I'm going to ask you almost 99% of the time to do a two-tail t-test. And you see how to find the two-tail t-test in a minute when we do the example. So there's an example data set. And in this data set, the first column is the participant ID, which is the number for each participant. The second column is the grouping variable. So it separates two people into two groups, those who use social media before bed and those who do not. And the third column is the average sleep duration for each participant. And then these are the example. These are the problems these are the questions for the example problem. What is the null hypothesis, the alternative hypothesis, the mean for group 1, mean for group 2, the mean for both groups, the variance for group 1, variance for group 2, the pooled variance for both groups, the standard deviation for group 1, for group 2, and pooled variance, the combined degrees of freedom, the t-statistics, the two-tailed p-values, the estimated Cohen's d effect size, the magnitude of that effect size, the percentage variance accounted for, which will be listed as R squared or R hat 2, which is R squared, and whether the p-value is significant or not, and then write up the results in the APA format. Whew, that's a lot. But don't worry, we'll go through it together. So I'm going to copy all this and paste it into the copy and paste it into the exercise sheet. You see here, there's also the answer sheet. So I have the answers available to you. Let's open this. Here's the data set. So some things off the bat. You see here, it says lecture problems exercise sheet. This is what we're working from. Here's the answer sheet where the answer is. You can click that at any point. And what else? These 3 sheets are for the in-class exercises. So don't worry about these for now. I just wanted to include that all in one single document, one single Google Sheet document, just so it's easier to like keep organized, just so we know that this is the document we're using for week 4 for both the in-class exercise and for the lecture exercise. Okay, let's copy and paste this here. Okay. Black, so it's easier to see. Drag this over. Okay. I'll even make these bold, so we can see which one is the question and which one is the response. And I'm holding Command on my Mac to do that. Okay. Let me make this larger so you can see it better. Perfect. Okay. So here's the data set. You see here that there's 28 people right here. Count 28 people. So 14 in each group. Here's the first group, the group that uses social media. So participant 101 to 114 use social media an hour before bed, and participant 115 to 128 do not use social media before bed. And here's the average sleep duration for each participant. So how do you read this? The first participant uses social media within an hour of bedtime, and they sleep on average 4 hours a night. The participant 117 does not use social media before bed, and they sleep an average of 7 hours per night. So you want to know, do people in this group sleep any less than people in this group? Based on your hypothesis, my hypothesis is yes, they should sleep, yes, because social media disrupts sleep. So the people in this group should sleep less hours on average than people in the no social media group. Okay, so let's fill this in. The first question, the null hypothesis is for the population, people who use social media within an hour of bed do not differ in sleep duration from those who sleep, who do not use social media. Remember, the null hypothesis is meaning there's no difference, no significant. That's what the null hypothesis is. The alternative hypothesis is what we're trying to prove in our research, what we're trying to test. So the alternative hypothesis is that people who use social media in an hour of bed have significantly less sleep than people media. Okay, the mean for group 1, the mean for group 2, and the mean difference for both groups. Okay, so this is where we have Google do the work for us. All right, you need to install add-on. Add-on is called XLMiner Analysis Toolpack. So what you do to install, you probably don't have on your Google Sheets yet. So what you do is you click on add-on, click get add-ons, and search for it, XLMiner, and it should come up like that. And you click on it, and then right here, it should say install. Mine says uninstall because I already have it installed. So what you want to do is click on install, and it should install pretty quickly. Let's stop that. So once you install it, and you click add-on, it should pop up here. So what I'm going to do, XLMiner Analysis Toolpack. I want to add it to the lecture so you could know how to find it. So the XLMiner Analysis Toolpack. Google Sheet. You see the spellings right. XLMiner Analysis Toolpack. Yeah. For this. So what you do is you go to Google Sheet, and instructions. Then click on add-on, then search, and search for this. Install. Okay. All right, let's get back to it, to our problem. Okay, so what you do is you go to data, add-on. So XLMiner Analysis Toolpack is basically a suite of different statistical tools that you can use with Google Sheets. This is not built into Google Sheets, so it's made by a different company. And so you see here, they have a lot of different tests, correlations, covariance, histograms, linear regression. All right, so what we want to look for is t-tests, two samples, assuming equal variance. Remember we said that we were assuming that both groups have equal variance in population. There's one for unequal variances, but we're not using that in this class. So you click on this. Okay, these are the inputs. You have to put the values for the first group. They call it variable 1, but just assume it says it's same as group 1. The range for group 2. You don't have to write anything for hypothesis mean difference. You don't have to click on this label. You could leave this at alpha level 0.05. We'll always use alpha level 0.05. And then you have to decide where you want this, what the output to be on your Google Sheets. Okay, so what's important is that you have to click on the values for the first group, and then click on the box here for it to input. So remember, I highlight all the values for the first group, which is the social media before bed group, right? So all these are sleep durations for the people in the group that uses social media before bed. So I just highlight the number for sleep duration. I click here, and it populates this C2 colon C15 means C2, right here, C2 is this column, colon means 2, C15, so C15. So from C2 to C15, that's what this means. Okay, for now we had to highlight the values for the second group here, and then click on highlight first, then click on the box, and then it puts in those values for us. Remember, we leave this blank, we leave this alone. For the output range, we want to tell Google where we want to put the output. So I'll click here because there's an empty space, and click output range, and then that's it. Then you click OK. Okay, I should probably mention this in the lecture somewhere. Instructions how to do this. Maybe I'll do it here. How to use. Okay. Use. Explainer in the example one. Um, open minor going to add on selecting and then two add-ons minor start. Okay, and two variable one range, variable two range, and output range. Two for variable one range. Highlight or select the values, the X values for group one, and click on the variable one range. Okay. Select the X values for group two and click on the variable two range for then output range. Click anywhere on Google Sheet. Need an empty cell Google Sheet. Then and put output range. Output range. Done. Okay. Fit on the page. I think that is so small. Okay, we just have to put that. Okay, let's get back to it. Okay, so we ran the tests, we ran the t-test. That's basically what we did. And then when we ran the t-test, it gave us this table, right? This table for our results. It's bold. And I'm gonna have you put your results in terms of 2 decimal places. So using these buttons to reduce the number of decimal places. Okay, that's good. All right. So now we can use this table to answer our questions here. All right, so what's next? The mean for group 1, mean for group 2, and mean difference for both groups. Okay, so group 1 mean equals, where is it? Right here, 5.64, 5.64. group 2 mean equals right here, 8. The mean difference for both groups, mean difference equals, basically just minus these two, 8 minus 5.64. Just have Google compute it, 8 minus 5.64. You get 2.36, right? 2.36. Delete this. All right, variance for group 1, variance for group 2, polar variance for both groups. Variance is this row. Variance for group 1 is 1.32. Group 1 variance equals 1.32. Group 2 variance equals 0.92. And poor variance, that's this one right here, poor variance equals 1.12. Poor variance is just the combination of the variance from both groups. And it's basically just the average. So you highlight both of these, you go down here, see the average is 1.12, which is the same value as the poor variance. So it just takes the average. The standard deviation for group 1, group 2, and poor variance. Okay, we have to do some calculations. Remember, the standard deviation is the square root of the variance. So for group 1, standard deviation equals group 1, the variance is square root of the variance is 1.32. Enter. So standard deviation is 1.148 or 1.15. 1.15. Group 2 standard deviation equals, double click on this, bring up the formula again, and delete the variance of group 1, put the variance of group 2, which is 0.92. 0.95 is the variance of group 2. The standard deviation of group 2, 96, rounding up. Okay, and standard deviation for poor variance equals, delete the variance for group 2. Look at the poor variance is 1.12. That gives you the standard deviation, which is 1.06. The combined degrees of freedom is 26. Combined degrees of freedom is basically the adjusted sample size for running this test. So remember this, the degrees of freedom, the df equals n minus 1 for both groups. So each group has 14 people, and so the degrees of freedom in one group is 13, because 14 minus 1 is 13. And the degrees of freedom in the second group is also 13. And then when you combine them, this is the combined degrees of freedom. 13 plus 13 is 26. That's how we get that number. Okay, so df equals 26. All right, t statistics is negative 5.88. So we don't have to do any computation here. Negative 5.88. Two-tail p-value. So you see here, this p is the p-value. There's two of them. So there's one type of t-test, and this is the other type. So you always use the two-tail, which is, you see here, it says 0.00 because it's reduced to 2 decimal points, but really the value is not 0. The value is some really small amount. But you can never write p-value equals 0 because there's no probability that you can never say there's no probability that the results aren't due to chance. There could be a very small probability, but you can never say there's no probability. So you can never incorrect write 0. So in this case, you could either write the very specific number like this, p equals this huge number, which don't do because no one does this. And since I'm asking for 2 decimal points, do p less than 0.01. That's the same thing as saying p. Same thing as saying this because it's less than this value. It's less than what we have space for. So we say p less than 0.01. Okay, Cohen's d effect size. This isn't on this chart, so we have to calculate this. So what we need to do is we need to go back to the formulas. Okay. Here it is. Remember, this is the formula for Cohen's d. Copy this. All right. So let's just fill this in. D equals the mean of group 1 minus the mean of group 2 all over the square root of the pool variance. So what I recommend is just copy this and paste it here. And then just replace these values. The mean of group 1 is 5.64. The mean of group 2 is 8. The pool variance is 1.12. Here it is. And remember, this is just text right now. Google is not going to compute this for us until we copy it and put an equal sign in front to start the cell. Then Google knows there's a calculation. And then paste the formula. The answer is negative 2.23. That's the magnitude of the Cohen's d effect size. Negative 2.23. Okay. All right. The magnitude of Cohen. Oh, okay. Yeah, you don't put it here. Put it. The Cohen's d effect size, you put it here. Where it's asking for. Okay, what is the magnitude of Cohen's d effect size? Is this small, medium, large? Let's go back to the lecture slide. You know, anything that is greater than 0.80 or extends beyond negative or positive 0.0 is a large effect. So this qualifies as a large effect. Right. Variance accounted for, which is listed as R squared. This is the other effect size measure. And let's go back. This is the one that we have to compute ourselves. And this is the formula for R squared. Let's copy this. Okay. Paste this. Equals. Oh, this formatting get messed up. This is really say R squared, like R hat. Okay, remember, just copy and paste this over again. Copy, paste this to the right side so you can start filling in the values. T, what's the T value? T value here is negative 5.88. Negative 5.88. T value again, negative 5.88. Again, all the answers are here for you, so you don't have to do anything. You have to plug it in. DF is the degrees of freedom. What is that value? The value is 26. What does this equal? Remember, Google won't compute it until we take this out and put an equal sign in front of it in a new cell. Copy this. Equals, paste, here's the value. This is the variance accounted for value, which is 0.57, no, 57, yeah. Or this is a percentage, so you could say 57%. Okay, based on the p-value for this test, we can conclude, is it significant or not significant? So remember the p-value, anything less than 0.05 is considered significant. So this p-value is less than 0.01, so even smaller, so significant. The way to write this in APA format is, okay. Let's go back and look at the APA format. Here it is. I'm gonna copy this. Use that thing right up here. The participants in the treatment group reported fewer episodes of major depression compared to participants in the control group over the past year. The mean difference in episodes of depression between groups was large and significant. Okay. The participants the participants in the group that uses social media before bed. And we're gonna put the stat there. Had significantly less sleep than the participants in the group that does not use the group that does not use social media before bed. Remember, you have to put the two. There was a large and significant between the groups. Sleep duration. Okay, you have to put the stats here too. All right, so we have to put the mean and standard deviation here. The mean for the social media group was what? 5.64. Standard deviation for the social media group was what? Standard deviation isn't, remember, standard deviation isn't listed here. But the variance is, and from the variance we calculated the standard deviation earlier. So standard deviation for the group 1 is 1.15. Okay. Here's the where you put the mean and the standard deviation for the second group. Mean equals 8 decimal points. Standard deviation equals, for standard deviation for group 2 is 0.96. There was a large significant difference between the groups in terms of sleep duration. All right. So what we do here is put the t value, put the degrees of freedom, which is equal to 26. T equals, t value here is negative 5.88. And you put the p value, p is less than 0.01. And you put the effect size measure, but right here, and we're going to use Cohen's d. You can technically also put the R-square variance accounted for, but I'm going to ask that you use Cohen's d for the sake of our assignments, because it's more commonly used. Cohen's d equals negative 2.23. Okay, that's how you do the write-up. So that concludes this lecture on hypothesis testing and using the t-test. I want to delete all this. So when you click on the exercise sheet, it's all blank and you can do it from scratch. Again, the results is going to be here in the answer sheet for you. So you could refer to it. The exact same results that we got earlier. Okay, back to the lecture. I think that's the last slide. Okay, well done.